So in the last class, we started discussing about the mathematics of asymmetric key cryptography, and we discussed Euler's phi function and primes as well. So the next topic which we will need extensively in asymmetric key cryptography is Chinese remainder theorem, which is called abbreviated as CRT. So why do we use this theorem and how does it help in asymmetric key cryptography, that we will talk. But before that, we need to understand that what does this theorem say and how does it work. Okay, so this theorem it is used to solve a set of congruent equations with one variable but different moduli, and those moduli are relatively prime. So it might sound confusing right now, but as we will move further, we will discuss the example and how do we use this theorem to solve these kind of problems, to solve congruent equation with one variable, so the things will be clear to you, right? So it will help us to solve a set of congruent equation with a set of congruent equations with one variable. So here, as you can see, we are finding out this this x variable is congruent to a1 mod m1 as well as a2 mod m2, and it is congruent to ak mod mk as well, right? So this single variable is congruent to a1 to a2 to up to ak, right? And this moduli is also different for each and every variable, right? So this is the thing which we will be talking over here while discussing this Chinese remainder theorem. So we need to find this variable which can be congruent with a number of variables with different moduli. Okay, so this variable will be same, but it will be congruent with many other variables having different moduli, right? So this is the thing we will be finding over here. So ultimately we will be looking for the value of x. We will be finding the value of x which again will be congruent to a number of variables. So how do we do this? We have a number of steps for finding out this variable x. Okay, so we will be discussing all of these steps in detail. How do we proceed to find out this variable x? So this is the example just to make you understand this theorem in a better way, and how do we carry out this variable x, or how do we implement this CRT, this Chinese remainder theorem, that we will discuss later in the later slide. So this is an example of a set of equation with different moduli, right? So here x is congruent to 2 mod 3, it is congruent to 3 mod 5, it is congruent to 2 mod 7. So we need to find a number which is congruent to all of these equations, right? So congruency means कि जब आप लोग ये find out करोगे x mod 3 and 2 mod 3, the result should be equal. Okay, so if you remember that congruence property, it says if two numbers are congruent with the some modulus, then it means the first number mod the given number and the second number mod given number, the result of these two equations must be same. Okay, then we say that these two numbers are congruent. So the solution to this set of equation, if we, as I told you that we will be discussing it later, okay, but uh, this is just an example just to show you that how these things work in CRT. So for this given set of equations, the value of x or the variable which can be congruent to all of these equations can be 23. Okay, so if you find, if you replace this x with 23, then you will be finding that 23 mod 3 and 2 mod 3, the result will be same. So if you find out 23 mod 3, the result will be 2, and 2 mod 3, the result will be 2. So both of the results are equal, they are similar. So we can say that x, that is 23 we are saying over here. So 23 and 2, they are congruent. Against which number? Against mod 3, right? So this 23 number, it satisfies all the equations. So first equation it satisfies. If we go for second equation, then we will see, if I put this 23 over here, so 23 mod 5 and 3 mod 5, the results should be same. So 23 mod 5 gives you value 3, and 3 mod 5 again gives you value 3. So the result is same, right? So 23 is also satisfying, 23 is satisfying this second equation as well. For the third equation, if we find out 23 mod 7, the result will be 2, and 2 mod 7, the result will be 2. So 23 is the number which is satisfying all these given equations. Okay, so 23 is congruent to 2, it is congruent to 3, congruent to 2 mod 3, then 3 mod 5 and 2 mod 7. Right, so we can say that this number is satisfying all of these equations. So now we need to find out that how do we find this number, how do we calculate this number which could satisfy all of these given equations. So to find out this number which can satisfy all of these equations, we use Chinese remainder theorem, okay, which makes this whole process very easy. So now we will understand, we will be finding out the steps which we can use to implement Chinese remainder theorem. So these are the steps which we follow to find out the solution which can be congruent to a set of equations. So what we do is, we start with finding this variable which is capital M. Okay, and how do we find it? We will be multiplying all of the moduli which are given to us in the given problem, right? So for example, in this problem, the modulus, or the moduli we are having is 3, 5 and 7, right? So first of all, we will be finding out the value of capital M by multiplying all of these modulus, right? So first step is this one. So this will be now a common modulus, right? Second step is, we will be finding out three more variables which we specifically for this kind of problem, we will be finding out three more values, or if we talk about the generalized version, we will be finding out k values, right? So the first value, which we call as m1, will be found out using this expression. So the value of m, which we have found in the first step, divided by the value of first modulus, right? Second, m2 will be found out the value of m, which we have found out over here in the first step, divided by small m2, which is the second modulus. Okay, and this process goes on. जितने भी हमारे पास मॉडुलस की वैल्यू, जितने भी मॉड्यूली की वैल्यू गिवन होंगी, उन सब के साथ हम डिवाइड करके up to mk we can find out. Now what we will do in the third step, we will be finding out the multiplicative inverse of m1 m2 up to mk. Okay, so जो second step में हमने m1 m2 up to mk solve किए हैं, we have found out their value. Now we have to find out their multiplicative inverses, right? And the multiplicative inverses will be found out using the corresponding moduli, right? So m1 का जब हम multiplicative inverse we will be finding out, we will be using the small m1. Okay, and for capital M2 to find out its inverse we will be using the modulus value as small m2, right? And we call these inverses as m1 inverse, m2 inverse up to mk inverse. Fine. Now this is the completion of third step. Last step is we find out the value of x. The ultimate thing we are looking for is the value of x. Now how do we find out the value of x using all of these variables which we have calculated till step 3? We will be using all of these variables by putting up their value into this expression. Fine. So we will be finding out the solution using this a1. A1 will be this variable, this one. This will be a2, this will be a3, a1, a2 and a3. Okay, this is small m1, small m2 and small m3, and capital M and capital M1, M2 up to mk we have found out in these three steps along with their inverses. So how do we find x now? We will be using this a1 into m1 into its inverse. Then we will add the same thing for the second variable, which is a2, m2 and m2 inverse, and all of these will be added. Okay, so this is corresponding to the first expression which we have. This is corresponding to the second expression, and this will be corresponding to the kth expression. And then we will be finding out its mod m. Okay, so this m will be the value which we have found out in the first step. So all of these steps, these might confusing right now, but once we will be doing the example, जो हमने previous ये वाला example किया है, इसको step by step when we will calculate it, then you will be able to understand it very easily, right? So now we will be doing it step by step so that this thing will become understandable. Okay, so first step is to find out the value of capital M. So in this particular example, which is here, let me erase it. Now we have to check the value of small m1, m2 and m3, right? And the value of small m1, m2 and m3 is 3, 5 and 7 respectively. So now we can find out the value of capital M, right? Which is 3 into 5 into 7. So our result will be 105. The value of capital M will be 105. Now the step 1 is completed. For step 2, we need to find out the value of capital M, capital M1, M2 and M3. Why? Because we are having only 3 expressions over here, right? So up to mk, we have to find out the value of M1 and M2 up to mk. Fine. So this M1 will be capital M divided by small m. So the value of here, let me write, this is M1, this is M2 and this is M3. Okay, and this is capital M. So M1 will be M divided by M1. Fine, which is written over here. You can see this expression, right? So now we can find out the value of M1, which is 35. Value of M2 will be M divided by small m2, which is 21. M3 will be M divided by small m3, which is 15 now, right? So now we have the values of M, then capital M1, capital M2 and capital M3 with us, right? Along with this small m1, m2 and m3, right? So all of these values we have now. Now next step is to find out their inverses. इनके जो हमने second step में values find out करी हैं, इनके inverses we have to find out. Now for finding out their inverse, we will be using the extended Euclidean algorithm, and we will first check whether the GCD of the numbers is 1 or not. If it is, then there will be a multiplicative inverse of the number. Fine. And this multiplicative inverse we have to find out against the corresponding moduli. So when we find out the inverse of this number, which is for the capital M, we will find out its inverse against small m1, which is this one, 3. Okay, so we need to find out the inverse using the expression which says 35 mod 3, right? So how do we find it out? Now the inverse of m1 corresponding to small m1, which we say as 35 mod 3. Okay, so we have to find out now the inverse of this 35, right? So what we will do, we will be applying this extended Euclidean algorithm. So if you people remember, we have this table for finding out the multiplicative inverse, in which we keep track of the remainders and this t value. Okay, because if you find out that GCD of the given numbers, this is 35 and 3, if it is 1, then we extend this algorithm and find the multiplicative inverse. So for the first step, the value of n over here is 3, and the value of a or b, you can call it any variable, so that is 35. So we assign the value of n to r1 and the value of a to r2, right? So in the first step, this is r1, this is r2, fine. So when we divide these numbers, the quotient will be 0 and the remainder will be 3. In the next step, what we do, we swap these numbers. Okay. So in the next step, R2 becomes R1 and R becomes R2. Now we will divide these numbers. So after dividing, we get the quotient as 11 and the remainder as 2. Fine. Again, we will be changing the number, the value of the numbers. So R2 becomes R1 and R becomes R2. Again, we will divide it. So after dividing it, we get the quotient as 1 and remainder as 1. Right. So this process goes on until we get this 1 over here. Right. So if it is 1, then that means GCD is 1, which means the multiplicative inverse exists, right? So for finding out the multiplicative inverse, we will be extending this algorithm, this Euclidean algorithm. So T1 is initialized as 0, T2 as 1. So for this step, when we find T is T1 minus Q into T2. If you people remember this, T1 minus Q into T2. This is the way we calculate value of T, right? For the first step, this will be 0. Why? Because T1 is 0 and Q is 0. So Q into T1 will be 0. So the value of T will be 0. So in this as well, what we do, we change the values. T2 becomes T1 in the next step and T becomes T2, right? So here this T1 is 1 and T2 has become 0 now. So again we find out the value of T for this second step. So which is 1 minus 0 into 11. So it will give you the result as 1, right? Again the values will be changed. Okay, T2 becomes T1 and T becomes T2. So for the next step, this will be 0 minus 1 into 1. So that will give you minus 1, right? again the values will be changed and you will calculate t. Okay, so this time it becomes 1 minus 1 into 2. So that will give you 1 plus 2. So the result will be 3, right? And the values will be changed, right? So here you can see this value and this value, they are same now, right? So this will be the multiplicative inverse, but negative value is not acceptable, so we will convert it into the positive number. So how do we do this? जो भी हमारे पास ये मोड की वैल्यू होती है, जो भी मॉडुलस होता है, we add this number to this value. Okay, so minus 1 plus 3 will give you 2. So the multiplicative inverse of m1, which is 35, is 2, right? So this thing we can find out if you find 35 mod 3 and 2 mod 3. Okay, sorry, you find out the multiplicative inverse as a into b, it must be congruent to 1 mod n, right? And we are saying अगर ये दोनों नंबर multiplicative inverses हैं, then this condition must be satisfied. Okay, so we can check for these given numbers 2 and 35. So you will be finding this thing as true. Okay, so A will be 35, B will be 2. 35 into 2 is 70. Okay, 70 must be congruent to 1 mod n. And here the value of n is 3, right? So if you find out 70 mod 3 and 1 mod 3, the result will be same. So 70 mod 3 will give you 1, right? And 1 mod 3 will again give you 1. So the values are similar. So we can say that they are multiplicative inverses. So after this calculation, there is always a way that you can tell your answer whether it is correct or not, right? Okay, so this is how we have found out the inverse of m1 corresponding to small m1, and this inverse is 2. Just like this, we will be finding out the inverse of m2 corresponding to small m2. Okay, now this small m2 is 5 and capital M2 is 21. So we'll be finding out its inverse. So the whole process will be repeated once again, right? And the inverse which we have found out is 1. So again we can check for it. Fine. So 1 into 21 will give you 21. So 21 mod 5 and 1 mod 5, they should give you the same answer, and that is 21 mod 5 will give you 1 and 1 mod 5 will give you 1. So that means this answer is correct. Fine. Now we are done with this finding out the inverse of m1 and m2. So just in the same way we can find out the inverse of m3 as well, right? So value of capital M3 is 15 and small m3 is 7. So its inverse will be 1 again. Okay, so the same process of extended Euclidean algorithm we have followed. Now we have the value of capital M, small m1, m2, m3, capital M1, m2, m3, and m1 inverse, m2 inverse, and m3 inverse. So we can put all of these things to this expression, which is this one, this last expression, to find out the value of x, right? So when we put all of these things in the expression, this thing, okay, so when you find out its value, then the result we get is 23. Okay, so 23, if you find 23 mod 105, the result will be 23 after all, right? So we have found out now the value of x. So if you put this value of x, which is 23, in any of this equation, so all of these equations will get satisfied. Okay, so that is the thing which we were talking in the first slide that I told you. Okay, so this single value of x, which is 23, is satisfying all of these set of equations which are having different moduli. Okay, and these moduli are relatively prime as well. Okay, so this is how we use this Chinese remainder theorem to find out a single number which can satisfy a given set of equations which are having different modulus. Okay, which are having different the modulus is different and the variable is also different. Okay, and if you apply, or if you use that number which we call here as x, so it will be satisfying all of these equations, right? So this is how we use this Chinese remainder theorem, right? Okay, one more thing, the application of this Chinese remainder theorem, it has several applications in asymmetric key cryptography, right? We will be using it. And another application of this is, this theorem is used to represent a very large integer in terms of a list of small integers, right? For example, what does it mean that we can represent a large integer in terms of a list of small integer? Now, uh, what do I mean while I say this? Say, for example, if we need to calculate, z as x plus y, where x is 123 and y is 334, but our system is able to accept only the numbers which are less than 100. So what we can do in this case, we can use the Chinese remainder theorem, which helps us to represent a large integer in terms of a list of small integers, right? So we will be replacing this 123 with many numbers which could satisfy the set of equations as this 123 satisfies. Okay, so this 123, if we write this equation, sorry, this value as 24 mod 99 and 123 mod 99, the result will be same. So 123 mod 99, if you calculate, the result will be 24, right? And 24 mod 99, the result will be 24. Okay, it can also be represented as this expression, this which is 25 mod 98, right? This can also be expressed in this expression. So just like this, we can represent this value of y, which is large enough, which is more than 100. We can represent this number as 37 mod 99, 40 mod 98, or 43 mod 97. So these are just examples. Okay, we can have many more expressions which could satisfy, which can be replaced with this value of y, right? Now this z has to be less than 100. Okay, just like x and y. So now if we use these value of x and y, this value of z becomes 61 for the first case, 65 for the second case, and 69 for the third case. So here we can see the value of z is also less than 100 now. Okay, so we can save, we can use the value of x, instead of 123 we can use multiple values of x, right? So we can see that these three equations can be solved using the CRT to find the value of z. Now these expressions we have to sort out. Okay, इन पे हम लोग CRT apply करके we can find out the value of z. So one of the acceptable answers using all of the steps which we have just discussed it can be 457, right? So this value of z will satisfy all of these set of equations which are having different moduli, right? So this is how we use Chinese remainder theorem. So in the next class, we will be discussing its one more example because this is confusing. I can totally understand. So we will be using one more example. So that will be a tutorial kind of session जिसमें आप लोग भी थोड़ा सा we will interact and we will be solving this given equation in the class itself. Okay, so that's all for the CRT right now. Rest we will do in the example.